On the agenda for today, we are going to be talking about basic electrical quantities. So let's begin our discussion with voltage, okay? So what I'm going to do first is I'm going to hit you guys with a mathematical definition that we will literally never use, okay? So I'm just putting it out there that you don't really have to understand it. We're going to look at the math and kind of look at that to have it tell us what voltage is in the context of this class, and we'll go along from there, okay? So I'm going to say that voltage, I'm going to call this voltage VBA, and we'll talk about that in a moment, is equal to the integral from point A to point B of E, which is the electric field vector, dotted into some differential line element, dl. Now, for those of you that have already taken Physics 202, this should look familiar, except a negative sign is mixed up in there, which I've fixed by changing the limits of my integration. For those of you who have not had Physics 202, this is the hottest of garbage, and that's perfectly okay. We'll talk our way through it. So another relationship, again, you would need to have had Physics 202 for this to make any sense, is the definition for electrostatic force, okay? So electrostatic force, F sub E, is just equal to Q, some charge, times our electric field vector E. So what I'm going to do is I am going to rearrange that second expression for electrostatic force and plug it into my voltage expression so we can see what comes out, right? So E is going to be replaced by F divided by Q. So we're going to have the integral from A to B of our electrostatic force vector divided by charge, dotted into a differential line element. And since charge is a constant quantity, we can actually pull that outside of our integration, leaving us with 1 over Q times the integral from A to B of the electrostatic force dotted into a differential line element. What is the integral of force times distance? Work. So from this definition, we can see that voltage is simply the amount of work per unit charge, because we're dividing by Q, required to move charge from point A to point B in a circuit. That's all voltage is. It represents simple energy transfer when we move charge from one place to another place. So that's our first definition. Work per unit charge required to move charge from point, excuse me, not paint, Now, our second definition, we are going to get simply by understanding what a line integral is. How many of you guys have had enough calculus to know about line integrals? About half of you guys, right? So Since our circuits in this class will all be linear, simple, conservative systems, that means that our line integrals should be path independent, meaning it doesn't matter what path we take to get from point A to point B, the voltage that we see is always going to be the same. So from that understanding, we can say that another definition for voltage is the difference in electric potential between 2 points in a circuit. So in a circuit, voltage is kind of similar to how we view gravity here on the macroscopic scale. I know that probably sounds like a very odd thing, but we have electric potential energy that describes voltages, and we have gravitational potential energy that describes things like weight and stuff in our large macroscopic frame of reference. Those analogs will continue on. So we have a thing in electrical engineering and circuits that we typically call ground, which is just a reference potential of 0. That is an arbitrary thing that we are just choosing and saying, we are saying this is 0 so that all of the other math works out correctly. That's nothing different than me saying, well, if I'm going to do an experiment measuring, I don't know, velocity of an object falling or something like that, I know that if I consider this table to be my reference and I move this stylus up here, m times g times h gives me the amount of potential energy, and the amount of potential energy has to equal the amount of kinetic energy when I let it fall, kind of thing. It's just an arbitrary reference point that we are making up, okay? All right, so this second definition, the difference in electric potential between 2 points in a circuit, is the one that we are going to wind up using the overwhelming majority of the time, because it really tells us how we measure voltage as well. How do you use a multimeter to measure voltage? You clip one lead to some point in a circuit, probably the red one. You clip the black lead to another point in the circuit, and then you turn the dial to measure voltage, and it gives you the potential difference between those 2 points, because that's literally what voltage is, okay? So the next thing I want to talk about is how we're going to represent voltages in our schematic diagrams that we're going to look at. So there are several different ways that we're going to do it, or that are possible. There are like 2 ways that we are going to do it. But I'm going to talk about multiple different ways because you guys might choose to supplement my lectures with watching videos on YouTube and all that kind of jazz. So representing voltages. All right, so let's start with another generic circuit element. I'm going to call this circuit element A. And so I'm going to say that the voltage drop across element A is 5 volts, okay? So I'm going to have a magnitude, which you guys should all be familiar with from your freshman series. And then the thing that's going to trip you up is we must also take into account a polarity. So I am going to arbitrarily choose the positive polarity to be on top and the negative polarity to be on bottom. So think about it as if I were measuring this with a multimeter and I put the red lead on the top terminal and the black lead on the bottom term, okay? So in order for a voltage to be fully defined for the purposes of this class, and in my opinion, they should teach you guys this in the freshman classes, but I'm a jerk, so whatever. You need both magnitude and polarity. If you do not have both of those things, you have not correctly expressed a voltage. So what would happen if I switched the polarities? What would happen on a multimeter? You get a negative sign, right, on the magnitude. So 5 volts positive polarity on top is the exact same thing as negative 5 volts positive polarity on bottom. 5 volts positive polarity on the left is the same thing as negative volts positive polarity on the right, etc. Anytime you want to get rid of a negative sign with a voltage, you simply swap the polarity of the terminals. What this literally means is that the positive polarity terminal is 5 volts higher in electric potential than the negative polarity terminal. So if you pull out a AA battery or AAA battery or anything, you'll see that it has a clearly marked plus and minus terminal. We know that the magnitude of the voltage provided by one of those batteries is 1.5 volts. So that means the potential at the short nubby end is 1.5 volts higher than the potential at the bottom broad terminal. So this is the American style of representing voltages. Our next style that we're going to look at have that same generic circuit element A, and we're going to give it a magnitude of 5 volts yet again. But instead of using a plus and minus polarity indicator, instead, I'm going to use an arrow. I'm going to do it in a different color here. So the tail of the arrow corresponds to the negative polarity terminal, and the head of the arrow corresponds to the positive polarity terminal. This is the European style. You will never see me do this except for right now to show you what it is. I'm just making you aware of it in case you watch a YouTube video from somebody that isn't from America, okay? They are going to represent their voltages like that. I personally find that confusing because as an American, when I see an arrow on a circuit diagram, I think current. Okay, so having voltages and currents represented with arrows just confuses the bejesus out of me. I just wanted to make you aware of the convention. If we wanted negative 5 volts, what would we do? Make the arrow go in the opposite direction. Easy enough. All right. Lastly, we're going to talk about the double subscript notation. So I am going to arbitrarily label this top terminal with a lowercase a and this bottom terminal with a lowercase b. And I'm going to say that VAB is equal to 5 volts. So this double subscript notation, instead of indicating the polarity with a plus and minus sign, indicates the polarity with the order of subscripts. So the first letter in the subscript is the positive polarity terminal. The second letter in the subscript is the negative polarity terminal. So VAB it equals 5 volts means that terminal A is 5 volts higher in potential than terminal B. VBA would then have to be negative 5 volts. So if we want to change the magnitude or flip the sign on the magnitude, we simply swap the order of the subscripts. Now, we're not going to use this particularly much in this class. We are going to kind of use it when we do nodal analysis, where we're going to assume that ground is 0. So we're just going to leave that second subscript off. But for those of you that go into circuits 2, when we start dealing with 3-phase circuits and we have terminals all over the damn place, we will use double subscript notation almost exclusively. Okay. All right, so before we move along to our next mini topic related to voltage, does anybody have any questions about anything we've talked about to this point? All right, so the next thing we're going to talk about then is how we supply voltage is in circuits. So there are going to be 5 different ways that we'll see in this class. I'm going to start with this one. So this is the symbol for a battery. Now you may also see the following variations. You might see it with an additional long line and another short line. So whenever you see something like that, it means it's a battery that contains multiple cells, okay? So the original symbol would be like a 9-volt battery that you go and buy at the grocery store. And this symbol would be like the 9-volt battery pack that you made by connecting 6 AA batteries in series in your freshman classes, okay? That's the difference. From a schematic diagram thing or point of view, it literally doesn't matter which one you use. But if we're going to be nitpicky jerks, technically a single long horizontal line and a single short horizontal line means a 1-cell battery. And if you have multiple long horizontal lines and multiple short horizontal lines, it means a multi-cell battery. Batteries are examples of DC voltage sources, okay? So next, and another thing, you might also see the positive polarity terminal explicitly indicated on the long horizontal line, and the negative polarity terminal would be indicated on the short horizontal line. And then, of course, we also need a magnitude, which I'm just going to call VS in this case. So this is our battery symbol. This is what most of you saw throughout the duration of your Engineering 120 class. I personally prefer this symbol, which is for a generic DC voltage source. We'll go ahead and put the magnitude on here as well. So it's simply a circle. And then the positive polarity terminal is indicated with the big plus sign, and the negative polarity terminal is indicated with the big minus sign. There is no ambiguity whatsoever, right? I prefer this one because it works for batteries and like the DC power supplies we have in this class and all that kind of good stuff. It's just a generic all-purpose symbol representing that DC voltage is being supplied by something, okay? The next one that we're going to look at is an AC voltage source. It is the exact same symbol as our generic DC voltage source, except that there's a little squiggle in the middle that's letting us know that this voltage varies in time. Now, before we move along to the other two, I want to point out that these are all examples of what are called independent sources. So what an independent source is it's a source that provides a fixed amount of something, in this case voltage, regardless of what is connected to the terminals of this device. So a battery is supplying 1.5 volts, whether or not it's in a circuit or in my hand, right? It's a fixed voltage source whose value does not depend on any external quantities. Now we all know that over time, a battery will discharge and its terminal voltage will drop. We're going to pretend that doesn't happen for the purpose of this class. Yes, ma'am. because the amount of voltage that it's supplying changes with time, but it doesn't change depending on what's connected to it. So our next two are going to have extremely similar symbols. I take that back. They're going to have identical symbols, but they're going to have slightly different ways of expressing the magnitude. So I'm going to go ahead and draw both of them on here. So let's make this first one a voltage controlled voltage source. Or VCVS. Okay. So we have a diamond shape for our element. The positive polarity and negative polarity terminals are indicated on there. Our magnitude is going to be given by K, which is some scaling factor, times some voltage Vx. Now, technically speaking, we could have DC and AC voltage controlled voltage sources, but we're pretty much just going to use the same symbol for both. Okay. So this scaling factor K is going to have units of volts per volts. So all this means is that the voltage that's being supplied by this particular source depends on a voltage elsewhere in the circuit. And then our right-hand element will be a current-controlled voltage source. Or a CCVS. And its symbol will be lowercase r times Ix, where lowercase r is a scaling factor that has units of volts per amp. So when we multiply that scaling factor measured in volts per amp times the current measured in amps, we output a voltage. So despite the fact that this is controlled by a current, it is a voltage source. We can see from the schematic representation that it is a voltage source because there is explicitly a positive and negative polarity terminal associated with this symbol. Okay, I'm pointing that out because all of our dependent sources are going to look practically identical. We need to be able to determine what kind we have by looking to see if it has positive and negative polarity terminals indicated, which is going to tell us it's a voltage source. If it has an arrow, which we'll talk about in a little bit, it'll be a current source. If the quantity that's controlling it is a voltage, then it's a voltage controlled something. If the quantity that's controlling it is a current, then it's a current controlled something. Okay. So these two are examples of dependent sources. They are the voltage provided by these particular sources is dependent on either a voltage or current elsewhere in the circuit. Okay. Now, I know that that's probably sounds quite confusing. We're not going to see these physically in this class a whole heck of a lot. Really, they're used to model the behavior of certain circuit elements. So like transistors utilize dependent sources in their small signal models and all that kind of stuff literally all the time. Like that's how you view them because they're a nonlinear circuit element, so it doesn't have a nice, neat relationship that we can play around with like resistors, capacitors, and inductors. So this class, we're just trying to get you used to seeing them, and then we'll learn how they're applied a bit later on. All right, so 5 different ways that we will be able to supply voltage to circuits in this class. Does anybody have any questions about anything related to voltage, either that we've talked about or perhaps that maybe you think I forgot to talk about? Hearing nothing, going to move on to current. All right. So let's talk about current and charge, because these two quantities are very closely related to each other. So mathematically, current is given by the derivative of the charge with respect to time, which means that current is the rate at which charge passes a certain point. We really get to just make that point up as we go in a circuit with respect to time. Now, we can manipulate our expression for current. So if we multiplied both sides by dt and then took the integral of both sides, what we would wind up getting is that charge is going to be equal to the integral of the current from some point in time t naught, which just represents a point in time where the charge was known, to some later point in time t. And we're also going to have to add q of t naught here. So we're taking into account that initial condition. So I do want to make something very clear here. I threw in this t prime notation here, okay? This does not mean derivative in this class. You guys have probably had classes before where if you had t prime, that meant take the derivative with respect to, or first derivative with respect to t. T double prime was second derivative with respect to time. Here, we're using t prime as a dummy variable representing time because t is in our limits of integration, and it would just be too damn confusing using the same symbol in both places. Okay. I will never use a prime notation in this class to indicate that you're supposed to take a derivative. I will always explicitly do a derivative like I did on the left-hand side here. D quantity by dt. So, because I see students tend to struggle with particularly this second expression, I want to work a quick example problem here. Okay. So let's say that we have current on our vertical axis, time on our horizontal axis, and our current is behaving as follows. It is going to increase linearly over this interval. Let's call this from t is equal to 0 to t is equal to 3 seconds. So let's just say explicitly that time is measured in seconds. Then it is going to stay constant for 2 seconds. So this will be 5. Then it's going to drop down linearly here. Let's call that 7. And then stay constant. Let's call this 8. While we're at it, let's define some things. So let's make this 1, 2, and 3 for simplicity's sake. If we were told or were able to measure that the charge at t is equal to 0 was equal to, let's call it 2 coulombs, how would we go about determining the charge at, let's call it t is equal to 7.5 seconds? So there are two ways that we could approach this. The first way, and in my opinion, the harder way, would be for us to express our current waveform I of t as a piecewise function. For this particular thing, I would consider this significantly more difficult than the way we're probably going to wind up doing it, because I can see that we have at least exactly four different parts of our piecewise function. So that means we have to describe how this current is behaving over the interval from 0 seconds to 3 seconds, over the interval from 3 seconds to 5 seconds, over the interval from 5 seconds to 7 seconds, and finally over the interval from 7 seconds to 8 seconds or 7.5, whatever we want. So we could do that. It'll involve a little bit of time shifting and all that kind of jazz. And then we would have 4 separate integrals to solve and then add those results together. Or we can look at this thing and recognize that since the integral simply represents the area under the curve, and my curves are triangles and rectangles, we can use 4th grade math to do this integral the easy way and just add the areas together. That's the way that I'm going to choose to do it because it's a lot less mental math on my part. Okay. So what is the area of this section here under the line from 0 to 3 seconds? 4.5 what? So current, actually, so I didn't, that's on me. Let me do something here. I did not remember to mention, so thank you for that. Current is measured in amperes, where 1 ampere is a coulomb per second, and charge is measured in coulombs, which is a fundamental unit. So when we multiply current times time, we should get something measured in coulombs, right? Okay, so 4.5 coulombs, right? So 1/2 times 3 amperes times 3 seconds should give us 4.5 coulombs. I agree with that. What about the area from the interval from 3 to 5? So 2 times 3 is 6, so 6 coulombs. What about the interval from 5 to 7? 4, right? So we have that triangular part, which is going to have an area of 2 coulombs. And then we have the rectangular part on the bottom. So I'm saying subdividing it into this triangle, and then this rectangle, we get 2 plus 2 is equal to 4. And then lastly, we only need out to 7.5. So what's this part? Area. 1/2 of a coulomb. Okay. So what should Q at 7.5 seconds be? So let's see. So 10 plus 5 is 15. But what about our initial condition? 17. Right? We have to remember to add initial known amount of charge that we were given as well. All right, so practically anytime you are given a graph in this class, it will be something like this, where it'll be made up of simple triangles and rectangles. If it is not a graph made up of simple triangles and rectangles, I will explicitly tell you what the function is. Okay. With regards to the amount of calculus that you're expected to know in this class, we'll go ahead and get this out of the way. Simple polynomial functions, so like squared and cubed and to the fourth power and all that kind of good stuff. Derivatives and integrals, easy enough, right? Simple sinusoidal functions, so literally just sine and cosine. I don't think we'll ever have to take the derivative of a tangent function in this class or the integral of a tangent function, but we will integrate and derive cosine and sine functions just a ridiculous amount later on. I'm not really sorry. Exponential functions, integrals and derivatives of exponential functions. That's about it. So polynomials, exponential functions, and sine and cosine functions, if you can integrate and differentiate those, you know all of the calculus that you need to know for this class. I would say 90% of the calculus that I'm going to give you for those things is literally just plug it into your calculator and let it do its job. Okay. So no integration by parts or anything fancy, weird stuff like that. Just meat and potatoes calculus for this class. Okay, so we've talked about the relationship between charge and current. We've worked an easy example problem that is absolutely something I've put on a test before. So now let's talk about how we represent current on a circuit diagram. So we'll have our generic circuit element A. And I'm going to say that IA is, let's make it 2 amps. And just for the sake of argument, I'm going to complete this by putting an arrow indicating the current is flowing down through the element. So when we were representing voltages, we needed to know both magnitude and polarity. When we are representing currents, we need to know magnitude and direction. So it is not fully specified until we have both pieces of information. If this particular circuit element has 2 amps of current flowing down, how much current is flowing up? Negative 2 amps. So if we ever need to get rid of a negative sign on a current, we simply change the direction in order to make the magnitude positive. That's the only way that currents are represented. Realistically, there's also a double subscript notation type thing, but I'm not going to worry about that here. We won't use it in this class literally at all, so I'll just leave it as this. All right, so let's now talk about current sources. So there are going to be 4 current sources that we are going to see. We have our generic DC current source. We have our AC current source. And these are both independent sources. And then over here to the right, we will have our two dependent current sources. So the dependent sources are always indicated by diamonds. Let's make this one a current controlled current source. That'll be CCCS. And so we will have K times some current IX, where K is a scaling quantity measured in amps per amps or unitless. And then over here to the right, we will have a voltage controlled current source, or VCCS, where we will have lowercase g times Vx, where the units on the scaling factor G is amps per volt. And once again, our diamond indicated sources are examples of dependent sources. All right, any questions on currents before we move on to the relationships between power and energy? Nobody's saying anything? Do you need me to let you continue writing, or am I good to let you continue writing? Okay. If you ever need me to slow down, just tell me to slow down also. Yes, absolutely right. So if the arrow is pointing up, current's flowing from bottom to top. The arrow is pointing to the right, current's flowing from left to right, etc. For some elements, yes. So that's going to be governed by what's called the passive sign convention, which is something that we're going to talk about here in about 4 to 5 minutes. There is a relationship between the polarity of a voltage and the direction of a current that tells us whether power is being absorbed or supplied. And effectively, that means whether or not we need to include or leave alone a negative sign. Yes, ma'am. That is a squiggly line because it's an AC source. All right. Am I free to move along to the next topic? All right. So now we're going to talk about the relationship between power and energy. So the symbol for energy is going to be W. And I'm going to write this out a little bit strangely. I'm going to say that the energy is the derivative of hold on, I'm forgetting how I wanted to do this. I could have written this down. Nope. Power, that's the problem, is the derivative of energy with respect to charge multiplied by the derivative of charge with respect to time. Because we know fundamentally that power is the derivative of energy with respect to time, right? Well, when I express it in this particular way, so the derivative of energy per charge, joules per coulomb, is just voltage, and charge per time is just current. So this is the exact same thing as the product of the voltage multiplied by the current flowing through a particular circuit. Our word definition, if you will, for power is going to be simply the rate of energy transfer absorbed or supplied by a circuit element. And then our definition for energy is going to be the integral from some arbitrary point in time t1, some arbitrary point in time t2, of the power absorbed or supplied by an element, such that energy is total amount of power absorbed or supplied over a fixed interval of time. All right. Simple definitions. P is equal to I times V, exactly what you guys learned in your Engineering 120 courses. Energy is just the integral of power, nothing ridiculous there. Now we get to the passive sign convention. Okay. Now, for reasons that I cannot ascertain, and this is my jackass coming out, students seem to find this difficult, and I really do not understand why, because it's pretty straightforward. Okay. So I'm going to describe the passive sign convention to you in the easiest way that I know how. Let's say that we have some generic circuit element A. And I'm going to draw a long set of terminals out of this element like so. And this element is part of some larger circuit, which is what those ellipses indicate. Let's say that there is a voltage drop across these terminals, so across element A, where the positive polarity terminal is on top and the negative polarity terminal is on bottom. Let's also say that there is a current flowing into element A, and the current is flowing into the positive polarity terminal. In this case, the power absorbed by element A is simply VA times IA. So when current is flowing into the positive polarity terminal, the absorbed power is I times V. The supplied power is negative VA times IA. Now, I want to be clear about something here. At no point have I said whether VA is a positive or negative quantity, or whether IA is a positive or negative quantity, because it is inconsequential. When current is flowing into the positive polarity terminal, we say that the absorbed power is positive I times V, and the supplied power is negative I times V, and then we plug in the numbers, and whatever we get is what we get, okay? In the opposite case, we'll take our exact same generic circuit element, part of a larger circuit. Here's VA. Now we're going to have IA flowing into the negative polarity terminal. Our absorbed power is going to be negative VA times IA, and our supplied power is going to be positive VA times IA. So, over the course of your in-class assignments, homeworks, exams, all that kind of good stuff, you are going to be asked to calculate the power either absorbed or supplied by circuit elements starting from today and ending with the final. Okay, this is going to be something that is going to show up over and over and over and over and over again. And I'm warning you right now that I am absolutely enough of a jerk to put the same answer on your exam, one with a positive sign and one with a negative sign, to force you to learn this stuff, or you'll literally lose like 4.5 points on a test grade because you didn't understand this thing. And that's going to show up on every single one of your tests, okay? So I'm giving you fair warning now. If you do not understand this, please ask. We are going to practice it religiously for the next several days until hopefully it becomes second nature. But there are some folks that just don't seem to catch it even after we've been doing it for 2 months. These are the rules. It doesn't seem confusing to me, so I don't understand why it's confusing to you. But then again, I am a jackass with a PhD and you are not. So this is the passive sign convention. Okay? So let's put this into practice by working one of your web work problems. We're going to work one that I am particularly annoyed with just because it's worded poorly. So the keyboard is not working. There we go. Let's look at homework 1. Let's see. This is just current and charge relationships. Bleh. Energy, power, current, voltage relationship, bleh. We could do this one, but I don't want to. This is you're given charge and you're trying to find current. That's easy enough. This is the one I want. Okay. So first, I want to indicate something here at the very bottom here where it says which of the DC sources above are absorbing power. What it actually means is which of the DC sources above are absorbing positive power. Okay. Because you could argue that all of them are absorbing power and all of them are supplying power, but that's not what it's asking you for. Okay. So it wants you to check the box of which of the sources are absorbing positive power. Okay. So let's take the time to draw this thing out. So this is homework number 1.5. Draw this kind of large. So I believe we had a voltage source, positive polarity on top. Current source, I believe, was directed to the right. Voltage source, positive polarity on top. Current source direction down. Current source direction up. And then voltage source, positive polarity on the left. So, and let's see what we were told. All right, so V1 was 14 volts. I2 is 2.5 amps. We're told that this is V2, which I don't, we were given that, so that's negative 2 volts. V3 is 16 volts. I3 is negative 1 amp. I4 is negative 1 amp. V5 is 16 volts. I6 is negative 2.5 amps. And this voltage V6 is 32 volts. All right. So just for the sake of argument, this is 1, 2, 3, 4, 5, and 6. So I want us to calculate power absorbed by each element. So let's start with element 1. So what's the voltage drop across element 1? 14 volts. What's the current flowing through element 1? Yes. Is that current flowing into the positive polarity terminal or the negative polarity terminal? It's flowing into the negative polarity terminal, which means we need to include a negative sign to get absorbed power. So 14 times 2.5 is 28 plus 7, 35. So it looks like negative 35 watts if my mental math is correct. Let's look at element 2. What's the voltage drop across element 2? Negative 2 volts. What's the current flowing through element 2? 2.5 amps. Is the current flowing into the positive polarity terminal or the negative polarity terminal? Positive. So because the current's flowing into the positive polarity terminal, we don't add an extra negative sign. And so we're left with -5 watts, and that 5 looks too much like a J for me, so let me fix that. There we go. Let's look at element 3. What's the voltage drop across element 3? 16 volts. What's the current flowing through element 3? -1 amp. Is that current flowing into the positive polarity terminal or the negative polarity terminal? The negative polarity terminal, which means we need to add a negative sign because we're calculating absorbed power. So that's going to look like positive 16 watts. Element 4. This one may be a little disagree. Now, to be clear, we have not yet covered Kirchhoff's voltage law, which if we had covered Kirchhoff's voltage law, this would be very easy. So we're going to have to rely on some stuff that we learned in Engineering 120 because the web work was written before I took over teaching this class. When two elements are in parallel, they have the same voltage drop across them, right? Well, I would argue that the 16-volt source is in parallel with the -1 amp current source, which means the voltage drop between this terminal and this terminal is 16 volts, right? Because voltage is simply the potential difference between 2 points, and we know that the voltage at this point is 16 volts higher than the voltage at this point because this voltage source is forcing that to be true. Okay. So that one was a little bit tricky, but I believe that we can understand why that voltage is 16 volts. So let's write that down. The current is, Walker, what's up? So the only way that I can explain that is with Kirchhoff's voltage law, which you guys have already had it. So we'll do a more formal explanation of it on the next class meeting, right? So if we have applied Kirchhoff's voltage law around, let's do this path right here, okay? I'm going to start at the bottom left. So the first thing that I see is the negative polarity terminal of the 14-volt source. So I'm going to have -14 volts. Then I see the positive polarity terminal of the -2-volt source. So that's going to look like plus -2 volts. And then I have a wire, which has a voltage drop of 0. And we'll talk about why that's true a little bit more on some Wednesday's class meeting. And then I have the voltage drop across the -1 amp source. I'm going to set this equal to 0 because I'm back down to my original point. So if I rearrange this algebraically, the voltage drop across the -1 amp source is 14 volts plus 2 volts is 16 volts if I include the effects of the 14-volt source. I could also do it by doing Kirchhoff's voltage law around this path, and I would also find it 16 volts, or around this path, it's going to be 16 volts regardless of the path that I choose. So whenever the two elements are in parallel, it's just going to be that because of Kirchhoff's voltage law, regardless of what path I choose. Did that clarify things? Okay. All right. So a little bit of heads up about what we're doing Wednesday, sorry. So our current is -1 amps. Is that current flowing into the positive polarity terminal or the negative polarity terminal? So here's the positive polarity terminal flowing into the positive, which means we're going to leave that alone and we're going to get negative 16 watts here. For element number 5, what's our voltage? 16 volts again. What's our current? Negative 2.5. Is that current flowing into the positive polarity terminal or into the negative polarity terminal? Into the positive, okay. So that means we don't mess with anything. So let's see, 32 plus 8 seems like 40 to me. And then lastly, we have element 6. So what's the voltage? 32. Current is negative 2.5 because it's the same current that was flowing through element 5. Is that current flowing into the positive polarity terminal or the negative polarity terminal? Negative polarity terminal, which means we need to we have 2 negative signs, so those are going to cancel each other out. 80 watts. All right. So I want you guys to do me a favor really quickly. First off, we can see that only 3 and 6 would be checked for this to be correct for my particular set of numbers for this problem. But what I want you guys to do is add up all those powers. Zero. Okay. So there's a little thing called Telegen's theorem that says that the sum of all of the powers absorbed in the circuit or the sum of all of the powers supplied in the circuit must equal to 0. It's not anything particularly fancy. That's just the law of conservation of energy. So, all right, so that is enough out of me for today. So it is 8:20, or excuse me, 9:20. So we have 30 minutes of class left. I would suggest that you guys work on the lab first. And then whatever time you have left, take that to work on the in-class assignment. If you have any questions about things, I'd be happy to answer them. Yes, sir.
No, can you just quickly go over why this is going from the negative terminal slash positive terminal? Which one is going to which? I'm trying to see.
Okay, so let's look at number 6 in particular. Okay. So this current, can I draw on your thing? Is flowing through this path. It hits the negative polarity terminal first.
It is flowing through this path because
that current source is forcing.
okay.
So this current source is driving current along this branch.
Okay.
And it's going to hit the negative polarity terminal first.
Okay.
When it's flowing, that same current is flowing around this way because these two things are in series. When it's through this 16-volt source, it hits the positive polarity terminal first.
So this goes this way,
Yeah.
but this is
So this one right here is flowing out of the positive polarity terminal, which means it had to flow into the negative polarity terminal.
okay.
Yeah, that's it.
So much.
So just a quick thing here. On your mini lab sheet, which is up on Moodle and all that kind of good stuff as well. The circuit diagram that I drew looked something like this, where you have your voltage source, which represents your DC power supply. You have current meter in series with your device under test, which in this case is literally just a resistor. Put this as DUT. And then I believe I have you putting your voltage measurement from here to here. I would actually suggest that you not do that. Okay. Instead, what a better place to put your voltage measurement would be directly in parallel with your device under test. The reason for that is that it will allow you to troubleshoot whether or not your fuse is blown in your multimeter for measuring current very easily. Because with this particular configuration, if you have everything turned on and your fuse is blown, all of your multimeters will read 0. Which means either you disconnect or you didn't connect things properly, which for this circuit is kind of hard to do, or you need to replace the fuse on your multimeter. So that's the way that I would prefer you put it together instead of the way that I tell you in the lab assignment.